if you're looking at this one here, like I get it, the Kong is a little big and this whole thing looks a bit silly. But if you follow the concepts, hopefully it actually does make sense, right? So it's like you've got an alien traveling by Earth near the speed of light. Both the alien and King Kong wish to measure the distance from A to B, right? So in other words, he's very big, but you just bear with me. It's silly, but it works. And so we've got some space buoys out here, right? Basically, we've just got some, they could, whatever, they're just little things sitting out there in space, far enough away from Earth. They're just, for all intents and purposes, they're stationary. Earth is stationary, right? It moves around, but we can ignore any motion around the sun and all that. It's relatively slow compared to the speeds we're talking about. So yeah, we got these buoys just sitting here, and they're a certain distance apart, right? And we want to measure that distance because we forgot to measure it before when we put these buoys out there in space. So we'll just call them A and B, right? Now there's a alien traveling by, which I forgot to put here, or the picture. I think I got one down here. So there's our little alien. He's traveling by here, right? So sorry, I forgot about that. But here's what we're going to do, right? How are we going to measure the distance from A to B when we've got this this little alien and a little flying saucer flying by at speed v, right? So what do? We say, well, we know that the distance is just velocity times time, right? We know that. So we're going to measure this distance, right? And remember, just like yesterday, we had the proper time and we put a subscript S for that for stationary, right? We're measuring something that's stationary in our reference frame, and we're going to put a subscript M if it's relativistic. That is, we're measuring something that's moving relative to our reference frame. So, because we're going to use the time it takes this spaceship to go from A to B, we're going to be measuring the proper length, right? Because these two buoys are stationary in our reference frame. We know the speed of the alien and his little flying saucer is v, and because that little flying saucer is moving, the time it takes, right, is tm. We're measuring the time of something that's moving in our reference frame, right? We're going to disagree on the time it takes. We saw that with time dilation before, right? But we're timing it, so it's we're putting that into the equation. Okay, so in the alien's inertial frame, I feel like there could be some little. We got our little flying saucer here. Right, in the alien's inertial frame, I don't know why I felt like I'm drawing something there, just to picture it. You have to really get into their reference frame, right? You have to say, okay, I'm in the alien's inertial frame. Everything is stationary inside this flying saucer, right? They're moving at a constant velocity. There's no acceleration, so they've got their own sort of coordinate system, if you will, attached to their right, to their spaceship, and it's at rest. What's happening in their inertial frame is the Earth and the space buoys are zipping by them at speed v, right? So that's why they're going to measure the length too between these two buoys, but they're going to be measuring the length of something that's moving relative to them. So that's why it's LM here, right? The length is of something that's moving. They're moving with, or everything seems to be moving with speed v once again. And they are actually measuring the proper time. They're measuring, right, because they are stationary in their reference frame while this is happening. So all I did down here is say, okay, we have two equations. We can call them 1 and 2 here. They both have the same v in them, so you could just set them both equal to v. And that's sort of what I did right here. And then just divide both sides of that by ls, and then multiply both sides by ts, and that gets you over here. And then you can go back to time dilation and those equations. Let me get rid of that. And we had the equation last time where this one here is slightly rearranged. The equation we had was for Tm equals 1 over this square root function. So if you manipulate that equation, it'll look just like this. And then you can take that and substitute, since you've got Ts over Tm here, not Tm over Ts. You can substitute that in, and that gives you this. And since we want it kind of in the same form as we had last time, you got this. And by all means, take your time, go through the math a little more, like on your own, work it out. For now, hopefully you can trust me that this is sound, and that the math works, and you end up with this equation very similar to what we had for time dilation. The only difference was if when we had that, and yeah, that's sort of what we got this one here from, right? We had the relativistic time, right, was equal to the whatever the stationary time was divided by the same factor here, right? And so the time was longer, right? The time was slower for something that was moving. But now we see it's actually the opposite effect with length. That is, the length seems to contract. It seems to get shorter for something that's moving. And that has really interesting implications. Again, if you take the inertial reference frame part seriously, and you say, well, that means for the alien, right, this is what they see. They see Earth and these space buoys get closer together. You'll know that this effect is in the direction of motion, right? So if this alien had some sort of, we said this was the into the page Z, or whatever direction you want to call it, and suppose X is the direction of motion, then you're seeing this length contraction, or they're seeing this length contraction in that direction. But if you want to call this Y and you want to call straight up and down Z, these two directions are unaffected. Right? And so that's kind of a neat thing that what they see is this versus, right, what Kong here sees. Again, just bear with the diagrams, right? But this is what Kong would see, or anyone on Earth would see, is, again, the space buoys, everything is normal, they're at rest, but we would see the length contracted here in the direction of motion. This thing would look squished in the direction that it's actually going, right? And as with time dilation, there's no correct reference frame. They're both inertial reference frames. They're both correct. And this works out. And it's, like I said, it's a really weird effect, right? I took a diagram, I think, from the textbook just to sort of show and remind you that as with time dilation, the effects are minimal. Right? Very, very, very minimal effects. You're not going to notice this at all in any way at regular speeds. You'd have to get pretty close to the speed of light. And this kind of gives you an idea. You'll note it's going the other way. Right? You'll notice that here you're saying, okay, the length that you would measure for something moving. So imagine we're seeing this spaceship go by. How much do we see the length contracted in that direction? Well, if you'd have to be going like, 0.2c before you get anything, you could barely notice it, right? And then as you keep going and going and going, and you can see here, and this is one of my favorite parts of this whole thing, is this end of the diagram, where you see this, that it approaches zero as you approach the speed of light. So the way I kind of think about that is imagine imagine the speed of light was more like, 100 kilometers an hour or something like that, right? So you get in your car and say it's capable of going maybe not perfectly 100 kilometers an hour, because we'll get to why that takes like an infinite amount of energy and all that. But what would happen when you get in your car and you say, oh, okay, I'm in Ottawa here or whatever. You get in your car here, and terrible car, and you're here in Ottawa, and you're going to go to TO, you're going to go to Toronto or whatever, and you start driving in this direction with, right, some speed, getting, approaching the speed of light, which now for our thought experiment is 100 kilometers an hour. So what happens is you start accelerating and start heading toward Toronto at this speed, right? For one thing, you notice the time dilation effect. So you notice all the people here, right, along the side of the road or watching you go by. They start to move in slow motion. Right, so you notice everybody just seeming to slow down as you get faster. But this says there's something else that happens as well, is that not only are you moving to Toronto faster and faster, or wherever you happen to go, but it moves closer to you. Right, so as you're in your car accelerating, it actually gets closer. The length contracts and it heads towards you. And if you could get all the way to the speed of light, the length contraction would be everything, right? It would be the distance to anywhere would approach zero. So the dimension that you were actually heading in, if you could go the speed of light, would cease to exist, right? The other side of the universe in that direction of motion, like the trip would be instant because the length would be zero. So for you, the trip would be, let's say, 0 seconds. You would just get there. The other side of the universe would come to you. Now, I mean, there's all sorts of reasons that you can't actually do that, but you can imagine if you could, it'd be pretty cool. Okay, our example here, a spacecraft measures 100 meters in length. So this would presumably be someone in that inertial frame. It travels by Earth at 0.95 c. What's the length of the spacecraft as measured by an observer on Earth? What is the width of Earth as measured by someone on the spacecraft? So we'll assume by width of Earth here we mean in the direction of motion, right? So for part A here, the key is that the length, this is LS, this is a length that's measured for someone who's stationary in this reference frame, is 100 meters. And someone on Earth, we assume we're all here, we would measure LM, right? We're measuring the length of something that's moving. So we can just use that equation that we just derived, which is LM equals LS times the square root of 1 minus V over C squared, which equals LS was 100, and this is 1 minus 0.95 squared. So this is one of the nice ways too, when you get the speed reported to you as a fraction of the speed of light. You'll notice like I just substitute in 0.95, because if you actually do that, right, if you do that here, you're saying, well, this is 0.95 c divided by c, that all gets squared, right? So it ends up just being 0. So it's kind of a convenient way to do problems like that. And then we end up with 31.2. Whoa, sorry, I can't write. All right, so this is an appreciable length contraction, but also note, again, this is pretty fast, right? 95% the speed of light. But again, it's not 95% length contraction, right? It's barely 70% length contraction for going 95% the speed of light. So even on that level, right? For part B, right? So just looking at the poll results, right? Like and then it's a spread. Most people saying longer, right? That the observer on the spaceship would measure a length that's longer for the Earth, right? That the Earth would seem bulged, if you will, sort of like that if they're going by. And it does feel that way, right? You always you innately want to say or feel like, no, this person's moving, right? I'm stationary, you're moving. And you really have to try to get out of that mindset. And you really have to say, look, for someone on the spaceship moving by Earth, right, they are stationary. They're in a spaceship that's not moving, right? It's just chilling out there in the middle of space, and the Earth is whizzing by them at 0.95 C. So if we take that for them they're stationary and Earth zooms by, then we can say then diameter of Earth, right? Or sorry, LS equals 1.274 times 10 to the 7 meters, right? So that's the diameter of the Earth, which is the proper length, right? It's the length that we would measure at rest here on Earth. And so that means LM, the length they would measure for the Earth, would be, well, it'd be the exact same factor that we found up above. Or let me just write the 1.274 times 10 to the 7 times the same thing, which we already know is 0.312, which equals 3.975 times by 10 to the 6 meters. So almost 4 million meters, or we could say this would be 3.975 kilometers. Now again, compare this to 12,000 kilometers, right? So it's, again, the width of the Earth is about 30% of what it appears to be for us, right? It looks pretty round to us, but what this observer would see would look more like that, right? They would see the Earth shorter in the direction of motion that they're going by. All right, so the simultaneity. So we will sort of a little bit of a new topic, but an important one, and one that always to me feels like it takes a second to even really appreciate, because it just seems like odd. But you gotta just take a second and sort of like get our bearings or whatever, just still appreciate, okay, if the world still makes sense or whatnot. So here we have observer 2 standing on the ground. Not sure why that swapped on me. Right, so you can see this. I think I had this diagram before. We have observer 1 in this trolley car moving at speed v, which we'll assume to be really, really fast. And observer 2 on the ground down here looking at that. And one thing that I feel like is important with this, let's assume that these people are rational actors, right? That is that they understand how to do math, right? They understand things like that. So, for example, if you look at light, let's say it's starlight at night, right? And you're here on Earth, and you've got one star over here that's 4 light years away, and you've got another star over on this side that's one light year away, right? And the light from both of these stars reaches you at the same time here on Earth, right? Which event would you say happened first? And that's why I feel this is important, just to, like I said, sort of get our bearings. Relativity is weird, but let's just, make sure we understand. Yes, absolutely. This event over here had to happen first, right? Or the light from that star had to start out reaching us 4 years ago, right? Whereas the star that's 1 light year away because a light year is the distance light traveled in a year, right? So that means, right, if we're looking at which event happened first, it's going to be this one. If we're looking at which event happened more recently, it's this event, right? Because we understand, we're rational actors. We can do the math. We can say, well, if the light's reaching us at the same time, and one thing is farther away, then that must have happened first. Probably something you don't appreciate in your day-to-day life, right? Because the difference is minuscule. But if you're looking, at the window and you see, a flower right in front of you and a house farther away, you don't think that, oh, actually the light from the house far away took longer to get to me. It feels like the light's instant, but even though it's technically not. So anyway, let's take this to an event. Okay, so we've got observer 2 standing on the ground. They see, and so what observer 2 sees, and this diagram hopefully shows it a little bit, is it doesn't really matter that it's lightning. It could just be a light that turns on, right? So observer 2 sees lightning, if you will, hit both the front and back of this trolley car at the same time, right? And how do they know, or how do they conclude that this happened at the same time? Well, again, because they're a rational actor. The light from, you can see at this point in time here, the front and back of the trolley car are equidistant, right? They're equal distances from observer 2. And then over here we see the light reaches observer 2 at the same time from both events. So it's only rational then to conclude, well, that means these two events must have been simultaneous, right? The lightning struck the front and back of the car at the exact same time, okay? And then again, observer 1 just continues to move off. So I made a couple notes because I think they're important here, right? They both agree that lightning hits the front and back of the trolley car. They both agree that light from the front of the car reaches observer 1 first. And they both agree that light reaches observer 2 at the same time. So that part's not really shown here, but if you start here, and I just, again, it doesn't really matter, but again, the light starts out toward here, but technically the light starts out in all directions, right? At the speed c. But because the trolley car is moving forward, right, you can sort of see the light here. So again, if you sort of overlay these, the light that would have started out here, right, is already there. And the light that would have started out back here, right, is still about here maybe. So it's reasonable then to say, well, yeah, the light that hit the front of the car would have hit observer 1 first, right? Or we can be sure that that's what observer 2 would see, right? It just seems like common sense. The question is, what about observer 1? What does observer 1 see in terms of these events? Does observer 1 say, yes, these events are simultaneous? Does observer 1 say, no, lightning hit the front of the car first, right? Again, assume this is a rational person who can do math. Or do they say, no, it must have hit the back of the car first? What say you? Polling results, bit of a mix. I think but the majority seem to be simultaneous, right? A and B first, and a slight hitting the front first. And the real challenge of this, I think this is essentially one of Einstein's like thought experiments, like, what would happen here, and what would they agree on, what would they disagree on. And he said, like, absolutely, observer 2, right, we agree on it, would say this is simultaneous. But observer 1, again, you really have to be in observer 1's inertial reference frame. Inertial is a very key word. They're not accelerating. As far as observer 1 is concerned, right, they're stationary. And so this part here is really the big key. Both agree that light hits observer 1 first. Well, observer 1 is in an inertial frame, so that means all the laws of physics hold, and observer 1 would say these events are not simultaneous. Observer 1 would say, no, lightning hit the front of the car first. right? Lightning hits the front, which I've labeled B, or is kind of part B in the diagram first. And again, from this here, we definitely agree that from observer two's perspective, lightning from the front of the car hits observer one first, right? And then you have to say, well, okay, let's, if we can, this, and this is where this is a bit deceiving, I always feel like, because the real point of this, and Einstein's kind of point was that events that appear simultaneous in one reference frame are not necessarily simultaneous. In fact, they're not simultaneous in another reference frame, right? Just period. Not that necessarily, they're just not. And the other thing is that they're both equally correct, right? There you go. So it's important. We'll write it down, and hopefully Apple will stop underlining all this stuff and making it seem obscure. But yeah, events that are simultaneous in one inertial frame are not simultaneous in another. Now, here's the other really important point here, though, right? Both observers are equally correct. Right? And that's where this thought experiment, and I've seen this, you'll see this in lots of textbooks, but I just feel like it's slightly misleading because it's presented, right? Even the way I worded it here, admittedly, is a little suspect, right? Observer 2 standing on the ground sees lightning bolts. I guess I tried to be pretty good here. Sees lightning bolts strike the front and back at the same time, right? And so I'm saying, look, this is observer 2's perspective, right? It feels like the correct perspective, right? I mean, it feels like, yeah, they're on the ground, the other observer's moving in the trolley car. But then you have to say, well, wait. From the observer on the trolley car's perspective, they're not moving, right? The observer 2 on the ground and the ground under them is moving, right? So you kind of imagine observer 2, let's see if I can. Right, if we try to draw this, right, well, they're in a nice stationary trolley car. And what do they see happen first, right? Now, also, it's worth noting, I suppose, that for them, in their trolley car or whatever, right, observer 2, which I'll just put like O2, well, where do they start out? They're kind of drawn side by side here in the first one, but if they seem to be going to the right, that means actually observer 2 would be going to the left, right? So we can say, well, they actually start out, right? Here's observer 2, right? I'll just put O2, you know what I mean. And they're actually going with this speed here, right, to the other way. Observer 2 and the ground and everyone is moving. Observer 1 is in a nice stationary reference frame. And what is, well, observer 2 has to see the light from here start out first, right? This event happens first. And maybe I could have drawn that a little bit more here. Okay. Right? This event happens first, right? And then if we go a little bit later, I don't know if I should try to go sideways here or down. I guess I went sideways on the other one. And then in the next frame, oh, you're not going to straighten it anymore? I love these Apple updates. Then what happens here? Well, now the light is a little bit further. Let's say it's actually reaching them there and here. And where would observer 2 be at this point in time, right? Maybe this thing is just turning on, right? Lightning is just hitting the back of the car right now, just striking it, right? And observer 2 would be probably about here, right? Here's O2. Let me move that down a bit. right? And a teeny bit later, let's see, we can get our third frame in here. We've got, oh, they did it that time. How about that? We've got the light from here that's gone all the way past them. And here's observer 2. Oh my goodness. So it would look something like that, right? So as I said, both observers will agree that lightning, or that event, in terms of the light from the event. So we'll say like this is event B or whatever, the front of the car. So both will agree that the light from this hits observer 1 first, right? And we can see that right here. And they both agree, and I thought that's a really interesting thing here as well. They both agree that light hits observer 2 at the same time, which again you can kind of see here as observer 2 is moving to the left from observer 1's perspective, right? It's just they disagree on the order of the events, and once again, no one reference frame is the, quote unquote correct reference frame. They're both in inertial frames. They are both correct, right? They just don't agree that they're simultaneous, and that's perfectly fine. Even if it's not perfectly fine to get this, to feel like it makes sense, that's okay, all right? Last thing here, and I think this is the longest one, really. Hopefully it was a bit shorter. Relativistic momentum. Okay. Obviously, you might expect just from the fact that the title's here, we do have to account for relativity when objects are moving really, really fast. We know classically for a moving object, right, the momentum, right, is mass times the velocity. And the velocity, right, well, that would be, delta L over delta T, both in the proper length and the proper time, right? That would be momentum. However, right, if you see an object moving in your frame, right, okay, you're measuring the proper length, right? You're saying I'm measuring, I'm at rest. Whoa. I'm at rest in this reference frame, right? And I'm measuring some object, doesn't really matter what it is, moving with some speed v here, right? Okay. So I'm definitely measuring the proper length if I'm measuring the time it takes, this object, just to make that a reference frame, right? If I'm measuring the time it takes for this object to go from A to B, we'll just deal with linear momentum, so some later time it's going to be here. But I'm not measuring the proper time, right? Remember, the proper time is the time measured at rest in an inertial frame. So when you picture this little object, right, you have to sort of imagine it's got its own little inertial frame with it. And for as far as this object is concerned, it's stationary. You're going to assume it's moving with a constant velocity, and everything else is moving by it with v going the other way. And also, you can imagine that it's got like a little clock here, right? And it's timing events, right? So how long it takes to go from A to B. If you are measuring this object here, again, you're measuring the proper length, of course. The A and B are stationary in your reference frame, but you're not measuring the proper time. You're not measuring the time as someone at rest in this object that's on top of this object. This was a ball. Imagine a little bug on the ball or something like that with a clock, right? You're not measuring that. So we just have to account for that. And this here is just the first one here is just the equation we developed for time dilation, but rearranged for the proper time. And then we can substitute that in here, because again, we want the proper time for momentum, but we don't have it. We're measuring, Tm. Oh, that was really weird the way that did that. So if we substitute that in here, then we end up with a nice new equation for momentum. And this is for us, right? We're measuring something going by. How much momentum does it actually have? And you'll notice the equation is virtually the same. The numerator anyway is still mv. We just have this extra bit on the bottom. And note, as with time dilation, right, it means the momentum is actually, or the relativistic momentum is actually greater than it was, right? Because this denominator is going to be less than 1, right? And I sort of skipped over this, but this sort of just gives you an idea if you actually start putting in the numbers. You can see that as you approach the speed of light, if you used classical, say Newtonian momentum, right, it would just keep going linearly as you might expect as speed increase, since it's, just to the exponent 1 in the equation. But relativistically, you can see the momentum is not exactly like that, right? It goes up quite substantially as you get closer to C. But also note, particularly if you're doing dynamics problems, note that at speeds less than C or much less than C, like the difference is minuscule, and there's no real need to account for this when you're dealing with regular, surface of Earth type velocities we deal with. And this also brings up the concept of the rest mass. I mean, all you really got to do is take this equation we just developed and bring the V out in front. That's sort of shown right here. So you just write it as m over this square root function, and then you can look at it, and again, it's just a perspective. Part of me is not really crazy about this. But if you want, you could look at this as like the relativistic mass, right? You could look at it as if it's more massive. Or to me, though, the most I would want to say is that it appears more massive, right? If you imagine a particle like we had up here, and maybe at B, right, is an actual wall. Right? Well, it's going to hit the wall, and depending on its momentum, right, it's going to make a dent or it's going to do some damage. And so you could look at that as saying, wow, it actually seemed like it had more mass, right? If you look at the damage it was able to do, it did damage as if it was more massive than someone, who would have weighed that thing when it was at rest would have measured. And then we can sort of define those terms. We can say, this here is the relativistic mass, and we can define the rest mass as when the thing has a speed of 0, right? In which case the numerator or the denominator here just is 1, right? So let's look at an example here. I throw a 450 gram football at 0.7 C. I don't know if you knew this. I played a little football back in the day. I think that was a typical speed. That's a joke. Calculate its relativistic momentum. How does this compare to its non-relativistic momentum? So we can basically just use the equation. If you want to we can say, well, momentum, P, right, is the same as it was before. It's just mv. But now it's going to be divided by 1 minus v over c squared. And if we put in the numbers here, the mass, we said, now again, anytime we get something like this, we can say this is the rest mass that we're actually given. So we can say, no, 450 grams, that's 0.45 kilograms, and v, we're told, is 0.7 c. I'll just write that sort of in meters per second, because I think we're actually going to want the speed here. Whereas in the denominator here, we can actually write that as 1 minus 0.7 squared. And just because I think it'll matter for part B, I have the numbers for both. So I said the numerator is 9.45 times 10 to the 7 when you multiply that through, and on the bottom we get 0.714. And that equals 1.32 times 10 to the 8. Kilogram, let's say. So that's a good amount of momentum, right? It's a good throw, I think. And I kept those numbers because if we want to compare this, right, how does this compare to its non-relativistic momentum? So part B, let's put that here, right? Well, if we looked at non-relativistic momentum, that is to say we're not going to account for relativity, then basically just we're not going to have this denominator here, right? That's the only difference. It would just be mv. So then we would say no denominator. Right? And so we would, and so note that yes, the relativistic momentum is actually more, right? And that sort of brings us a little bit to this last question, right? Explain the reason it's impossible for an object with mass to travel at the speed of light. And I'll just go back here for a second because you can imagine if you were just doing this the regular way with dynamics, Newtonian dynamics, that is, and you were trying to remember we looked at, recall that, impulse, right? Equal the change in momentum. Right? Which means you need a force. So, right, to change momentum. Right, so if you were trying to calculate, if you go back to this one, right, and you were trying to calculate, well, how much force do I need then, right? So if I gave you an amount of time, you've got a football that's stationary right now, right? How much force do I have to apply for some given time? You could calculate what that force needs to be over, let's say, 1 second to give it this momentum. But if you were doing non-relativistic momentum, right, you'd get a lower number here. You'd say, oh, that's the force, right? But in fact, that force needs to be greater, right? Because the actual momentum, the relativistic momentum, is actually higher than that. And more importantly than that, as you can see here, right, if you, or better yet, look at the equation, right? If you look at the momentum, if you wanted to put in c here for your speed, if you want to actually get to the speed of light, well, if this is c, right, then that just becomes 1 minus 1, which is 0. So the denominator of this thing would be 0, which means the momentum would be infinite, right? So as v approaches c, right, p approaches infinity, so you would need an infinite amount of force. I guess I could say and or time Right. Since you're looking at impulse, I suppose you could say, oh no, I'm going to apply a regular force, but then the time would have to be infinite that you're applying the force for, or the force would have to be infinite, neither of which is very practical.